So far we have discussed the convexity, the operations that preserve convexity, the first and second order condition of the convexity of a function, and now we will briefly explain what subgradients are. So this is not a comprehensive course in subgradient methods, but we'll briefly cover subgradient. So because later on we will be using algorithms like subgradient descent, stochastic subgradient descent, and a special algorithm known as PGSS, which is used to solve the SVM problem. So to be able to cover the theory for that, we'll just like briefly discuss what subgradients are, and we'll discuss them in more detail as they are needed. So let's see what are subgradients. So let's assume there's a function f, which is a mapping from n-dimensional vector to a scalar, and it's not necessarily convex. Then the subgradient of the function f is any vector g such that f of y is greater than or equal to f of x plus g transpose times y minus x. So the g is a subgradient of function we'll just denote it by subscript g. There is a subgradient of a function at point x. So any vector g that satisfies this property that f of y is greater than or equal to f of x plus g transpose times y minus x for all y in the domain of the function f is actually the subgradient of function f at x. At x, at the point where the function f is not differentiable. When the function f is differentiable, let's suppose if the function f is differentiable in Nord's domain, then the subgradient is simply the gradient. Right. So we can write it more mathematically, more compactly as the subgradient is any vector g that satisfies this property at point x for all y in the domain of function of f. Now the set of all subgradients at point x denoted by del f x, that is a set of subgradients, is known as subdifferential set. Subdifferential set is a set of all the subgradients of the function at point x. So this is equal to a set of all gradients. This is an n-dimensional vector such that f of y is greater than or equal to f of x plus g transpose times y minus x for all y in the domain of function f. So the subgradient of the function f at point x is any vector g that satisfies this property, and the set of all possible g's that satisfy this property, the set of all possible g's, is known as the subdifferential set. To view it, what it means is that the affine function given by fx plus g transpose times y minus x is global affine underestimator of the function. So let's consider this is a function f of x. Then at this point the function is not differentiable because, as you can see, there's a kink over here, so this function is not differentiable over here. So the subgradient is any vector g So this is one of the subgradients. Likewise, here, this is one of the subgradients. Also, this is another subgradient at this point, but this is not a subgradient, right? Any vector g, which makes, let's suppose this point x1, this is point x2, then this is f of x1 plus g transpose y minus x. So this, so if f of x1 plus g transpose y minus x1 is a global underestimator of the function f, then this g is a subgradient. So this is one of the subgradients, this is another subgradient, but this, any g, so let's name it g prime. So g prime results in f of x1 plus g prime transpose y minus x. It's not a global underestimator of the function f, and that's why it is not a subgradient. So subgradient should satisfy this property. And now look at the optimality condition. Let's talk about the optimality condition. So we discussed if f is convex, then the f of x star is a global minimizer. That is, here you can consider that this inf means minimum. For the purpose of the structure, you can just consider that this inf means minimum. It implies that the gradient of the function at x star is 0. So any point x at which the function of is the gradient is equal to 0 is a global minimizer, right? In case the function is differentiable. But what about the non-differentiable convex functions? So in case of non-differentiable convex functions, the condition of optimality becomes that 0 should belong to the subdifferentiable set. So if 0 belongs to the subdifferential set of f at x at point x, then this x is a global minimizer. Of the non-differential convex function f. So at points, so for any function that is differentiable, the subgradient is just replaced by the gradient. So there is a unique gradient at any given point. Whereas if function is not differentiable, then at a single point there can be infinite number of gradients. For example, we can consider a function f of x is an absolute value of x. So this function look like so for x, we can write this function as f of x is equal to x for x greater than 0, negative x for x less than 0, and 0 for x equal to 0. Now, this function is not differentiable at point x equal to 0. For x greater than 0, the subgradient is equal to the gradient of the function, which is equal to 1. For x less than 0, the subgradient is equal to the gradient of the function, which is equal to negative 1. At this point, at f equal to 0, there are infinite number of subgradients. For example, this is one of the subgradients. All these are valid subgradients. So any gradient, any value between negative 1 and 1 is a subgradient of the function at point 0, because at this point we can guarantee that f of y is greater than or equal to f of 0, which is 0, plus some value lambda, which is negative 1 and 1, times y minus x, where x is 0. So f of, we can replace by mod of y is greater than equal to lambda times y. So any lambda between negative and 1, between negative 1 and 1 will satisfy this condition. So that's why at point, even though the function is not differentiable, there are infinite subgradients for the function at point x equal to 0. So that's all we needed to know about the subgradients for the purpose of this lecture. So one of the important things to note down from this lecture is that 1, the subgradient is of the function f at x, not necessarily convex function, is any vector g such that f of y is greater equal to f of x plus g transpose times y minus x for all y in the domain of the function f. This is one. And second thing is that in the subdifferential set of f at x is a set of all vector g such that this condition holds. And third, the optimality condition if the subdifferential set contains a vector of all zeros, that is, if there's a g which is equal to 0 belongs to a subdifferential set of f at x, then that x is a global minimizer for a convex function. This you can also check if f of y is getting equal to f of x plus g transpose times y minus x. So although this holds for any subgradient at f equal to this holds for any subgradient at x that satisfies this property, but if g is 0, then what we get is f of y is getting equal to f of x for all y in the domain of the function f, and that's why x is a global minimizer. So that's all we needed to know about the subgradients to be able to derive the next algorithm to minimize the L1 regularized least square loss function.